In this video, I'm going to discuss the Lycoming / Allied Signal T-53 turboshaft engine. First thing I'd like to point out is the name. It's often referred to as a Lycoming T-53. This engine was originally developed by Lycoming, but eventually was sold to Allied Signal. So you'll see both versions of this that are out there. This engine produced under two different nameplates. Here's the overall view of the T-53 engine, and this is a turboshaft engine designed to be used in an aircraft such as a helicopter. This can be compared to something like a turbojet or turbofan engine, where a turbojet or turbofan engine is designed to produce thrust by accelerating a mass of air. The T-53 engine, as a turboshaft, is designed to, after producing expanding exhaust gases, it's attempting to extract as much energy as possible from those expanding exhaust gases to drive, in this case, a rotor blade. Turboshaft engines are very, very similar to turbopropeller engines or turboprop engines. In that case, the energy is being extracted to drive a propeller. Both of them are functionally the same. The difference is what is attached or how they are attached at the front. And if I go down to a view where we can see the front, I'll come back to this a little bit later, but you can see the shaft output here at the right side. And so a shaft would be connected here. If this was a turboprop version, you would have some kind of a propeller attachment, typically in the form of a flange or a spline mount for the propeller itself. If I go back to the overview, this engine, just like all turbine engines, can be divided roughly into two major parts. The first is the cold section, which is made up of the inlet and the compressor, which is here on the right. Now in this one too, the output shaft gearbox is included in this area because it happens to be in the center of the inlet. And then the hot section on the left is made up of the combustion chamber, the turbine, and the exhaust. And so I'll look at each of these in a little more detail with some close-up pictures. But this is your cold section on the right, hot section on the left. The last thing this engine has is it actually has two gearboxes. Earlier, when I talked about the cold section, was the output shaft gearbox. There's also a second gearbox down here at the bottom. This is the accessory gearbox, where things like the starter generator, fuel pumps, oil pumps, hydraulic pumps, all those kind of items would be attached to the engine. So let's zoom in on the cold section. So here, the cold section, the air, the intake air, actually comes in around the output shaft gearbox. So this area labeled A is where air is able to enter the engine around the outside of the gearbox. Item P, this area that's cut away, is the output shaft gearbox. And so that's taking the rotary motion from the very last turbine, and the turbine's spinning very quickly. It's a gear reduction. It's reducing the speed, increasing the amount of power that is available to the shaft. And we'll talk about that when we get to the turbine section at the end. But air enters, and the first thing it does is the air is going to go through a stationary set of vanes right here, known as inlet guide vanes. Okay, so these are going to guide the air into the first stage of the compressor. So these are not part of a compressor stage. They're purely smoothing out the airflow before it enters the compressor. Now this engine has a compressor that's actually made up of two different types. The forward half of it is a axial flow compressor. The aft half of it is a centrifugal compressor. And it kind of cuts off part of the compressor in this picture. We'll have to look at it in another picture in just a minute. But there are 5 stages of axial compression, 1, 2, 3, 4, 5, and 1 stage of centrifugal compression. So in total, it's a 6-stage compressor. So the way this works, air enters the compressor section, and each stage of the compressor is made up of rotating segments. So item labeled C right here is the first stage of compressor blades that are rotating. And then the other part of that first stage are the compressor vanes, okay, or stators. So we have blades and stators, and the blades are going to accelerate the air rearward. And then the stators, item D that I circled second, those are going to form a bunch of little divergent ducts. And those divergent ducts are going to convert the velocity. So the velocity that's imparted in C is kinetic energy. And then D, the kinetic energy, is going to get changed into potential energy in the form of pressure as that air goes through those divergent ducts. And an air or fluid passing through a divergent duct, the velocity decreases, the pressure increases. Then they're going to go through a second stage of compressor blades and a second stage of stator vanes, and a third stage, and a fourth stage, and a fifth stage that are all part of the axial compressor. And these are all on the same shaft. They all rotate together. Finally, the air, after exiting the fifth stage of the axial compressor, it enters the impeller, which is item E of the centrifugal compressor. And whereas the axial compressor blades are accelerating the air rearward, the impeller in the centrifugal compressor is going to accelerate the air outward. And so it's still doing the same thing. A compressor is a stage, a rotating section that increases the velocity, and then a stationary section that changes that velocity into pressure. So the rotating section here is going to increase the velocity, but now it's going outward instead of straight back. And then it's going to enter, and you can just barely see them here on the left side, is the diffuser. And the diffuser forms those divergent ducts now that convert that kinetic energy in the form of velocity into pressure, and again, in a divergent duct. So if we look at our next picture, let me go ahead and close this one down. And now we're going to look at the hot section, but I'm going to kind of wrap up my cold section discussion here. So now we can see, let me get my little thing out of the way. Here is that last centrifugal compressor stage where the air is being accelerated outward, and then it's entering this area here, and also shown down here is our diffuser, and that's those divergent ducts that are going to reduce the velocity and increase the pressure. And so when you have a compressor like this, as with any compressor, the way you figure out the overall compression ratio is to multiply each stage together. So if we have 5 stages, you would say those first 5 stages of axial compression, if they had an equal pressure ratio of 2, say we call it 2, you would have, let me change my pen color to something you'll be able to see better over here. Let's try black. You would have 2 times 2 times 2 times 2 times 2, or that's equal to 2 to the 5th. But then when we get to the axial compressor, the centrifugal compressor, a centrifugal compressor has a much higher compression ratio in a single stage. Oftentimes they're anywhere between 4 and 8, 4 and 8, 4 to 1, 5 to 1, 6 to 1, 7 to 1, 8 to 1. So if this centrifugal compressor had, we'll say, a 6 to 1 compression ratio, we would then have to multiply that times the pressure ratio of that. So if our each axial stage had a compression ratio of 2 to 1, we would go 2 to the 5th which equals 32 times 6. If we multiply that times 6, it gives us a 192 to 1 compression ratio. That's an extremely high one. So my numbers in my example, I was just shooting off the hip, are very, very high here. We wouldn't normally have a 192 to 1, but it was for illustrative purposes only. So I'm gonna get rid of all these. And now we're going to move into, now that we've wrapped up the cold section and the compressor, I'm going to start looking at the hot section. The hot section is what's making up most of this screen. And so after the air leaves the diffuser, so the air will come out here and it's still considered cold. Now it may be upwards of 400 or 500 degrees because of the compression, but that cold air is going to enter my combustion chamber, and it's going to flow around the outside here, and a little bit's going to go in. There's a little opening right here. It's kind of hard to see just because of its size. Let me just put my palette down here. But right here at the base of this T-shaped, this green T-shaped item is a fuel nozzle. So a little bit of air is going to enter that. That air is going to travel down the nozzle, and it's going to mix with fuel. At the same time, fuel is going to get sprayed in here. And you can see it on the bottom as well. Here's this opening. Now this nozzle should be a little further to the left. It's going to go through the nozzle, mix with fuel, and come out. And those are the areas where the fuel is going to be added and mixed with the air. So the fuel is going to be atomized by the fuel nozzle, which we have here. Fuel gets to those fuel nozzles through the fuel lines, which are H, and that fuel and air mixes, but that's a very small amount of the fuel, roughly 20%, of the air. The rest of the air is going to make its way through this combustion liner. There's little holes in it in several places, and that's going to form kind of a cool barrier on the inside of this. So we'll have fuel and air, roughly 20% coming out of our nozzles, and that's going to ignite, and then we're going to have cool air along the sides here coming up this way. And so now that, and there's even cool air that kind of comes in around this area as well. That's going to prevent those combustion gases from touching the metal and potentially melting the metal. And it's also going to start to mix as it goes further down. That fuel and air and the rest of the air is going to mix back together. So by the time we get to the inlet to the turbine, which is down in this area, it's cool enough that it's not going to melt those turbine inlet guide vanes. So that fuel and air is mixed, fuel's atomized, mixed with about 20% of the air. The other 80% of the air is used for cooling. That's going to be expanding rapidly due to combustion. And then it's going to move forward, and now the air will begin entering the turbine section. And this one's a little bit different than if you looked at the CJ610 turbojet. We have two turbine stages, but now they are not all hooked together. So the exhaust or the combustion gases are going to go through these turbine inlet guide vanes right here. That's going to smooth it out. It's also it's a convergent duct. It's going to try to speed it up a little bit. And then it's going to go and it's going to come in contact with these turbine blades right here. And the turbine blades, this first set of turbine blades, are connected through an outer shaft to the compressor section right here. And so that first turbine is known as the gas generator turbine. It drives the compressor. It also drives the accessory gearbox. Okay. And that's extracting just enough energy from that exhaust or that combustion gas before it becomes exhaust gas. It's extracting just enough energy from the combustion gas to drive the compressor and drive the accessory gearbox. Then the combustion gases, as they continue to expand and travel through our turbine now, they are going to enter another set of vanes right here that are going to smooth out the air. And again, they're convergent ducts, little convergent ducts. They're going to speed it up. And then that air is going to come into contact with this second turbine stage here. And now this turbine stage is not connected to the first turbine stage or the compressor. So if we draw this, we have concentric shafts. So you have this compressor section, or this turbine section here, that has an outer shaft that goes to the compressor. This rear turbine, I'll re-outline it in blue. This rear turbine, that has an inner shaft that runs through the middle, and it runs all the way up to that accessory gearbox at the front of the engine. And so that spins independently and drives the gearbox. And that turbine, which is known as the power turbine or free power turbine, its purpose is to extract as much of the remaining energy as possible from the expanding combustion gases and drive that gearbox at the front of the engine, which is going to drive the output shaft. In the case of this engine, that's a turboshaft. Or if it was a turboprop, it would be driving the propeller. Once the gases go through there, they have actually lost the majority of the energy of expansion. So to drive those other, the rotor or the propeller. Now the hot gases, what's remaining of the energy in them, is going to travel through the exhaust, which here is, you can see, different from our turbo. It really doesn't have, it's actually more of a divergent duct. It's really, we're not trying to get thrust out of it, it's just to get hot exhaust gases away from the engine and exhaust them out. We do have an exhaust cone, that's K right here, and there is a bearing. This is housing bearings in here, and there's various bearings throughout the engine. And then it's got an exhaust duct. The label M down at the bottom here is this outer duct. So you have an exhaust duct and then an exhaust cone in the middle. And then from there, the exhaust gases exit the aircraft with fairly minimal velocity. And just as an example, our King Air, which is a turboshaft or turbo propeller aircraft, if you look at the thrust produced by it, the free power turbine is driving the propeller gearbox, and that propeller is doing the majority of the thrust, upwards of several thousand pounds of thrust. They do include the thrust from the exhaust, and so you get several thousand pounds of thrust from the propeller. You get about 15 pounds of thrust that they add on from the exhaust. And so it does contribute, but it's negligible. So that kind of covers the end. So that shaft that's coming down the middle, remember, it's going to run from that free power turbine at the back, which is in orange here. Here's our free power turbine back here. That's going to be connected to a shaft that runs all the way up the middle, and it drives this gearbox up here to P, which reduces the rotational speed, increases the amount of power that's given out through the output shaft here, or in a turboprop, it would be the output prop mounting point.